Hi there, this is the last film about molecular shapes. It's called Examples of Shapes 2, and it follows on from Examples of Shapes 1. And this deals with more three-dimensional molecules, whereas the ones we looked at in Examples of Shapes 1 were all flat or two-dimensional. So hopefully by the end of this film you'll have had some practice at drawing electron dot diagrams and using them to decide what shape some three-dimensional molecules will have. So we'll be looking at all the three-dimensional shapes we looked at before in the first two films. Okay, so here's a tetrahedral geometry. We're going to look at an example of one of these. So I'm going to use a nice simple example, CH4. We've got to draw the electron dot diagram first. So we've got carbon in group 4 and we've got hydrogen in group 1, and there's 4 of them. So that's 8 electrons or 4 pairs. Okay, and if we draw the electron dot diagram for that, we'll join all the atoms to the central atom using single bonds, fill all the outer shells. Well, hydrogen can only hold 1 pair, so they're full already. Carbon's got 4, so we're there. We've got 4 charge centers around the central atom here, right? They are these single bonds. Okay, so in other words, as well as having 4 charge centers, we've got 4 bonding pairs. Okay, and every time you have 4 bonding pairs, as it said in the film Molecular Shapes, you're going to have a tetrahedral geometry, and as you might already remember, the angle between these 4 bonds is going to be 109.5 degrees, and this is just another way of showing it here. So 2 of them flat on the page, 2 bonds flat on the page, 1 coming out towards us and 1 off into the background. Okay, so you can't draw these 4 flat on the page, which is why this one isn't in the planar film, it's in the three-dimensional film. Okay, moving on. Let's have a look at an example of a trigonal pyramid. Well, a common one is the one that is drawn here, and that's ammonia. So let's look at ammonia. Ammonia's got nitrogen, which is in group 5, hydrogen, which is in group 1, but there's 3 of them. So there's 8 pairs. So once again, we're going to join all the atoms to the central atom using single bonds. We're going to fill all the outer shells of all the atoms. Hydrogens are done because they can only hold 1 pair. Fill the nitrogen's shell. How many pairs? 8 electrons, but that's 4 pairs. Sorry. So 8 electrons, 4 pairs. And we've used those 4 pairs. So we've got 4 charge centers around this nitrogen. Okay, there they are. There's a lone pair and 3 single bonds. So now, although we've got 4 charge centers, we haven't got a tetrahedral geometry because there are only 3 bonding pairs and 1 lone pair this time. Okay, so in other words, compared to methane, where there was an atom up here, we've now got a lone pair there, and now this becomes one of the corners of our polyhedron, right? The nitrogen is the corner, so it's like a tetrahedron except it's shorter, okay? And this is called trigonal pyramidal. So every time, as we've said before, we get 3 bonding pairs and a lone pair, we're going to have a trigonal pyramidal shape. Okay, moving on. Non-linear. Now, why is this one in the 3D film? Because if you think about it, if I've got 3 atoms, like this hydrogen, oxygen and hydrogen, I can always draw them flat on a piece of paper. It doesn't matter how I arrange them with respect to one another, they're always going to lie on one plane. And that's what this diagram shows. Like with the tetrahedral diagram earlier, where something was in the foreground and something in the background, these 2 bonds can be drawn on the same plane as one another, or in other words, flat on the page realistically. Okay, let's see what's going on here and why it's similar to a tetrahedron and the trigonal pyramidal, and why it's been included in this 3D film, even though it's a 2D molecule. Okay, H2O, we've got hydrogen in group 1, and there's 2 of them, and we've got oxygen in group 6, so that makes a total of 8 electrons, or 4 pairs. So as well as having these 2 single bonds, we're going to have 2 lone pairs on the oxygen. Okay, and now if we look at this, we've got 1, 2, 3, 4 charge centers around the central atom. 2 of them are bonding pairs, 2 of them are lone pairs, So this always gives rise to the non-linear or the bent or the V-shaped. Okay, the reason I've included it in this film is just to show you that those lone pairs, if you draw the bonds flat on the page, the lone pairs would come out one towards you here and one in the background over there. Okay, they are not, they're affecting the shape of the molecule because they're stopping this bond angle being linear. If there was just the two bonding pairs, we'd have a 180-degree bond angle. So the lone pairs are influencing the shape of the molecule, but we don't include them when we consider the shape of the molecule. So in other words, this isn't a tetrahedron, it's non-linear. Okay? So that's about it. That's all the examples of shapes. Hopefully, now that you can do this, you can start to consider what effect these shapes will have on the polarity of molecules. And that's the next set of films you watch, which is basically about intermolecular forces and how polar bonds can make polar molecules and give rise to dipole-dipole forces and other forces, in fact.